Hello, math students. Mr. B here once again. All right, we're going to continue doing applications of quadratic equations and look at motion in a gravitational field. So physics tells us that on Earth, the height above ground of an object acted on by a gravitational force will be equal to negative 16 t squared plus v naught t. So the h is the height above ground in feet, the t is the time in seconds, and v sub 0, or v naught as some people call it, is the initial upward velocity of the object in feet per second. Right, here's the problem we're going to solve. An object is thrown upward with a velocity of 40 feet per second. How long does it take for the object to reach a height of 20 feet? And when does the object hit the ground? All right, let's write our formula down. It's h equals negative 16 t squared plus the v naught t. So here the v naught is given to us as 40 feet per second. So 40 t. What is the problem asking? It wants to know how long does it take. So we're looking for t. T is the unknown here. And we want to know how long does it take. What is the time when the object reaches a height of 20 feet? So that's what h is. I should erase h. I'm going to put 20 feet there. 20 feet. Now, let's solve this. This is looking very quadratic to me. I'm going to move some terms around to make this look nicer. I'm going to add 16t squared to both sides, and I'm going to subtract 40t from both sides to give 16t squared minus 40t plus 20 equals 0. Now I see that there's a common factor in all these terms. I'm going to divide both sides by 4. That's the greatest common factor here. And if you do that, you end up with 4t squared minus 10t plus 5 equals 0. All right, we're going to use the quadratic formula here. You could use AC method, but I don't think you'd get very far because we need to find two numbers that add to negative 10 and multiply to be 20. And of course, those numbers don't exist as integers. All right, so let's use the quadratic formula, which is, in this case, it's going to be t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we see that a is 4, b is negative 10, and c is 5. So for us, t is going to be, well, the opposite of negative 10 is positive 10. Plus or minus the square root. Now b squared, negative 10 squared is 100, minus 4, and then the a is 4, and the c is 5. All right, and we're going to divide all that by 2a, so 2 times 4. All right, so let's start cleaning this up a little bit. This is, the square root is 100 minus, well, 4 times 5 is 20, times 4 is 80, so it's 100 minus 80. That's the square root of 20, all over 8. So square root of 20, that's square root of 2 times 2 times 5. So we can see that we've got 4 underneath. We've got a pair of 2's. We can write this as 2 square root of 5. That'll make our answer look a little nicer. All right, so this will be 10 plus or minus 2 square root of 5 over 8. And I see a common factor in all the pieces here, so all the terms. So 2 goes into 8, 4, 2 goes into 10, 5, and 2 goes into itself once. So the nice, clean, exact answer is 5 plus or minus the square root of 5 over 4. That's the exact answer. That's the time that the object is at 20 feet above the ground. We see there's two answers. We could add or we could subtract. We might want to get an approximate answer, and I've got those on my calculator here. If you subtract, you get about, it's not, it's going to write a negative number. It's positive. It's positive 0.69 approximately. The other number is about 1.81. These are in seconds. So why is this? Well, you've got the ground here, and you've thrown the object up. It reaches some maximum height and comes back down. At some place in the middle there, it's 20 feet. And when it's going up, it reaches 20 feet at 0.69 seconds. And when it's coming down, it's 1.81 seconds later from when it was originally thrown upwards. A nicer graph would be to write the height versus the time, which gives you this parabola. This is not the trajectory of the object. This is just height versus time. And here's maybe the 20 feet. And these two places here are the times. This is the 0.69 seconds. And this one is the 1.81 seconds. Does that make sense? I hope so. All right, this sort of gives us a clue toward the second question, which was, at what time does the object hit the ground? Well, it started at the ground at 0, and then it went up and then back down, and here's where it strikes the ground, right here. We'd like to know the time for that spot there. So, at least that spot on the graph. Again, this is not the trajectory. This is not, the object went straight up and then straight back down, according to the way the problem was described. All right, so part B is where the height is 0. So we'll have 0 equals negative 16t squared plus the 40t. And we've got to solve that quadratic. I think we can do it by factoring, actually. Let me get things looking nicer by maybe dividing dividing both sides by, how about negative 8? If I divide both sides by negative 8, that's going to make it look nicer. 0 will equal 2t squared minus 5t. That looks nicer, doesn't it? Maybe I'll even throw the t terms on the other side where we normally like to see it. Something like that. 2t squared minus 5t equals 0. To factor this, it's simple because there's just two terms. There's a common factor of t. And if you pull a t out, you'll have 2t minus 5 inside the parentheses here. And then the zero product rule is going to tell you that either t equals 0 or 2t plus 5 equals 0. So the first one, that was right here. That was our t equals 0 when we initially threw the object upwards. The other one, let's solve that. I'll subtract 5 from both sides. We'll have 2t equals negative, oh, no, I'm sorry, I wrote a plus sign here, but that wasn't right. Right, in the parentheses, it's minus. So, minus, that's going to make life a little better. I'm going to add 5 to both sides, and then divide by 2, and get t equals 2.5 seconds. Exactly. So, that is what time it is when the object hits the ground later. Now, does this time seem to make sense? It's a little bigger than the 1.8 seconds, which is good, and it's not way bigger than the 1.8. So I'm kind of confident that the 2.5 is correct. All right. Another way to check it would be to put it back into the original equation, but I think it's right. So I'm going to quit here. We'll see you for the next problem. Bye now.